Hello, lovely humans! In today's episode, we are tackling gradient descent. Woo! All right. So gradient descent is a foundation of machine learning, and really what it does is helps us find the minimum of a function or the smallest value of a given function. And the reason why it's useful in machine learning is because really what machine learning is doing is it's taking a set of known data, typically, and then you basically are guessing a solution, and then you find the difference between the guessed solution and the actual solution, and you call that, it's called the cost function. Sometimes it's called the loss function as well. And the goal is to make the difference as small as possible so that your prediction is as close to the actual value as possible. And then you can set loose your machine learning algorithm to go do new data that you don't know as much about. So we use gradient descent to figure out how to minimize the difference between our prediction and our actual value. And so this also is a topic that comes up a lot in physics and engineering. Really what it is just finding the minimum value of a particular function. And what I love about it is that it uses derivative calculus to do something super useful. Okay, so to understand what gradient descent is, let's look at a couple of simple examples. Let's look at an example. So if I plot y equals x squared, where we have y on the vertical axis and x on the horizontal axis, then my graph is going to look something like this. Oh, very pretty parabola. I'm so proud of myself. And so the derivative of a particular function tells us how this shape changes as x changes. In other words, what is the slope or the rate of change as we move along different values of x? And so what we do is we take the derivative to give us an equation, which then allows us to draw a picture so that we can actually better understand how the slope is changing over x. So to do that, we take the derivative of y with respect to x, or d dy of x, which gives us 2x. Oh, look at that. We can plot that, no problem. And so I make my second graph over here of y prime versus x, and I'm like, oh, look at that. Boom, that should have gone through the origin. Oopsies. We'll try that one more time. No. Okay. So let's see here. So it's gonna go through the origin. Yeah! Woo! Okay, party time. All right, so what our question is not, well, what's the derivative, but what's the minimum of this function? So one thing that's really interesting is that you could say, well, at a minimum or a maximum, the rate of change of y is 0. In other words, it's flat. Boom. And so that tells us if we set the derivative of y equal to 0, we can solve for the x value. And we're like, oh, look at that, that's so easy. 0 equals 2x means that x must equal 0. And so we can say, okay, well, the minimum of y happens at x equals 0. And then if we wanted to figure out what that minimum value of y is, we just take our value for x at y min, and we plug it back into our equation for y. So we would get y equals 2 times 0. Oh, boom. Oopsies. That's silly. Y equals 0 squared, which still gives us 0. So the minimum of y is 0. But we could also do this for, let's say, a maximum, where if our parabola was flipped, in other words, we had y, we'll say y2 equals negative x squared. Our derivative of y2, we're going to get dy2 dx equals negative 2x, and then that's going to be like this. Oh, boom, through the origin. And so in this case, we still get x equals 0. However, we now have a maximum instead of a minimum. And we would know that by looking at the graph or by looking at the equation. Okay, pretty straightforward, right? Let's do a few harder examples. Okay, Oh, the other thing I wanted to show you too, what color do I want to pick? Let's do orange. Okay, so let's say we have an equation, y3 equals x squared plus 20. What now? What? Okay, well, dy3 dx, or the derivative of y3 with respect to x, is still just going to be 2x. And so our orange derivative, it's an official math term, has the same shape as our original equation. And again, if we solve for the minimum of this new equation by setting the derivative of y equal to 0, or y prime, these two are interchangeable, then we get x equals 0. Ooh, let me do that in orange. X equals 0. And again, we plug that in to we plug that in for x to solve for y3 to get the minimum of y3. So we get y3 equals 0 squared plus 20. Can you all see that? Yes, okay. So then we get the minimum of y3 is 20. Boom. So that's how this can change. So even though our graph moved up a little bit and the minimum of y is not 0 anymore, we can still use the same technique. Yay. Okay, now let's do a little bit harder example. Okay, so let us say that you have, let's do x cubed. Okay, or yeah. All right, so now we have y equals x cubed, and we have an equation that looks like that. And now we can take the derivative and we say, okay, the derivative of y with respect to x is going to be 3x squared. And so now we have a derivative, or y prime over x, that looks something like that. It might be a little bit more narrow, but it's fine. You get the picture. And again, we could say, okay, well, what is the local minimum of this function? We do the same thing. We set the derivative equal to 0 and we solve for x. Again, it's pretty trivial. Words. 3x squared, and we get x equals 0. And we plug that back in and we get y equals 0. Bada bing, bada boom. Not too complicated. But one thing that is interesting, when you look at the slope of this graph, it's not a straight line anymore. And we can read that for some information. And so basically what this is saying is for negative values of x, y is decreasing until it gets to 0. And then for positive values of x, it is increasing. And so here we see we have a large negative value of y for large negative values of x. And as x goes to 0, y also goes to 0. And then as x increases, y increases as well. Pretty cool. Okay, so let's do a more interesting example, and then I will release you with a little bit of a challenge. Okay, so, whoop, notes, flip page. Okay, so this equation is going to be y equals x cubed plus 20x plus x, and it has a picture like this is y on the vertical, x is on the horizontal. Our picture looks like boop, where this is negative 20. Okay, so now we take the derivative and we want to find the local minima and or maxima. Ooh. Okay, so we get y prime equals 3x squared plus, oops, that was supposed to be squared, plus 20x times 2, which is going to be 40x plus 1. Oh, boop. Okay, and so now I don't want to plot this by hand, so I made it earlier. So when I graph y prime over x, I get a parabola like that. Okay, that's a little funky, but hopefully you get the picture. So this is a bit of a different situation, because now all of a sudden, when we set this equal to 0, oh, this is going to be a huge pain to solve. So 0 equals 3x squared plus 40x plus 1. And this is why my algebra teacher made us memorize the quadratic formula. So we have to solve for x, which gives us x equals minus b plus or minus square root b squared minus 4ac divided by 2a, where this is a, b, and c, divided by 2 times 3. Okay, so you would solve this to get the values of x, where y prime equals 0. The good news is that one of them is 0, and the other one is not 0. But you can solve this equation to find those. But basically what I want you to understand is that there's actually a local minima at x equals 0 and a local maxima at x equals something between negative 20 and 0, which you solve by this one. And so, yeah. So doing the derivative, setting the derivative equal to 0 can get us both, and we want to look at a picture to figure out which is which. Okay, so I hope that is helpful in figuring out what is gradient descent doing. Really all it's doing is taking our equation for that difference between the predicted value and the known value, and it is taking the derivative of that equation and then trying to find where that equals 0, and so it can find the minimum. Okay, so the challenge that I am leaving you is I'm gonna write it in purple because it's special. I want you to find the local minima or maxima, we'll see what happens, of this equation. Y equals x to the 4th plus 10x cubed plus x squared plus 7x minus 3. Okay, and it doesn't have to be exact. Plotting it is fine. So what you would need to do is take the derivative of y with respect to x, dx, and then you can plot that and look for the places where this equals 0. So, little hint, this one had 2, this one might have 2 or more. We'll have to do it to find out. Okay, so I hope that was helpful. Machine learning is all over the place, and I think it's really important to understand how things work at the very fundamentals. So please let me know if you have any questions on this topic or in calculus in general or about math. Yes, and I will see you next time. Okay, bye!